Today I start about one important topics related to vector space, especially in linear algebra. Okay, we start about finite dimensional vector space. We also going to discussion of that topics finite dimensional vector space. Okay, we write it now. A vector space is called okay is called finite dimensional is called finite dimensional if it has a basis consisting of finite number of vectors. If it has a basis, okay, consisting of if it has a basis consisting of a finite number of vectors of a finite number of vectors. Okay, then what happened? Then we also discuss here. Okay, we discuss that means in each basis the dimension of v. Okay, in each basis for v we call the number of the unique number of vectors. Okay, the unique number of vectors, unique number of vectors. Okay, in each basis, in each basis for v, each basis for v is called the dimension of v, is called the dimension of v. Okay, and is denoted by is denoted by dimension of v. Understood? And then what happened? Okay, and obviously a vector space that is not finite dimensional is called infinite dimensional. A vector space, okay, that is not finite dimensional, it's not finite dimensional, is called infinite dimensional. Okay, then we also discuss that means finite dimensional vector space. Finite dimensional means that means finite, it has a basis contain finite numbers of vector. Okay, so now we going to discussion of that. Okay, discussion of that means in this way the vector space 0, the vector space 0 has dimension 0, has dimension 0. Okay, and the vector space fn has dimension n. We erase our portion and going to further discussion of that. The vector space fn, the vector space fn has dimension n, has dimension n. Okay, the vector space in this way, the vector space m cross n if, okay, has dimension mn, has dimension, okay, mn. Understood? And the vector space pnf has dimension n plus 1. The vector space PNF has dimension n plus 1. Okay, and the vector space of complex numbers, okay, has dimension 1. Okay, the vector space of complex number has dimension 1 over the field of complex number. Over the field of complex number. Okay, the vector space of complex number, the vector space of complex, the vector space of complex number has dimension 1. Complex number has dimension 1. Okay, and over the field of real numbers, over the field of real numbers, okay, over the field of real numbers, the vector space of complex number, the vector space of complex number has dimension 2. Complex number has dimension 2. Understood? So in this way we also discuss so many finite dimensional vector space. Okay, so now we erase that portion and going to discussion of one important corollary related to that topics. Okay, okay, we write here corollary. Let V be a vector space with dimension n. Let V be a vector space with dimension n. Okay, and now we write here number 1, any finite generating set for V. Any finite generating set for V, okay, contains at least n vector, contains at least n vectors, okay, and a generating set for V contains exactly n vector is a basis for V, and a generating set for V, a generating set for V, okay, a generating set for V that contains exactly n vectors, okay, n vectors is a basis for V, is a basis for V. Okay, next we also write it in P. Okay, any linearly independent subset of V, any linearly independent subset of V, okay, that contains exactly n vector that contains exactly n vectors, okay, is a basis for V. Is a basis for V. Understood? Now we write in option C, every linearly independent subset, every linearly independent, every linearly independent subset of V, okay, can be extended to a, can be extended to a basis, can be extended to a basis, okay, for V. Understood? Now we're going to prove of that, okay. We write proof here, okay. Now let beta be a basis, let beta be a basis for V, okay. We marked it 1. We erase that portion and going to further discussion of that. Let G be a finite generating set. Let G be a finite generating set for V. Okay. Then what happened? Then some subset. Okay. H of G is a basis for V. Then some subset H of G be a basis for V. Okay. And H contains exactly, H contains exactly n vectors, then okay, and then since a subset, okay, since a subset of G contains n vector, subset of G contains n vector, okay, and G must contain at least n vector, okay, at least n vectors. Then what happened? That means if G contains exactly n vector, if G contains exactly n vectors, okay, then what happened? Then H equal to G, okay, then H equal to G, okay. Then what happened? H equal to G. Understood? So that G is a basis for V, so that G is a basis for V, okay. Then G is a basis for V, okay. Now we're also going to discussion of that in this way. That means we mark this B, okay. Then what happened? Let L be a linearly independent subset of V, independent subset of V. Okay, containing exactly n vectors, containing exactly n vectors. Okay, then it follows from replacement theorem, it follows from replacement theorem. Okay, it follows from replacement theorem that there is there is a subset h of beta. There is a subset h of beta. Okay, containing n equal to 0 vectors. Okay, such that L union H generates V. Okay, L union H generates V. Then what happened? Then thus H equal to phi. Thus H equal to phi. Thus H equal to phi, and L generates V, and L generates V. Okay, since L is also linearly independent, since L is also linearly independent, then what happened? Then L is a basis for V. Then L is a basis for V. Okay, understood? Now we're going to discussion of part C. Part C. If L is a linearly independent subset of V, if L is a linearly independent subset of V, okay, containing m vectors, okay, then the replacement theorem assert that assert that okay, then that replacement theorem assert that there is a subset H of beta containing exactly n minus m, vectors such that okay, L union H generates V. Okay, now L union H contains at most n vectors. Okay, then therefore L union H contains exactly n vector, contains exactly that means n vector. Okay, by 1. Okay, by 1 we prove that. Okay, if L is a linearly independent subset, then replacement theorem there exists H, then L union H contains at most n vector, and therefore by part A, obviously here we write by part A. Okay, this one. Then what happened? Then L union H be basis be a basis for V. Okay, so we also discuss this important corollary related to this, that means finite dimensional vector space. Okay, so we erase that portion and going to discussion of some theorem. Okay, related to that topic we discuss some theorem. Okay, so we erase that portion and going to discuss some theorem. We write here now this one, this set x square plus 3x difference 2. Okay, and here 2x square plus 5x difference 3, and here minus x square minus 4x plus 4. Okay, this one is a basis for what P2R. We also discussed this one in earlier. Now we just write this one is a basis for P2R. Okay, you also might be check it. We also discussed in previous class. This one is linearly independent set and obviously generate because this one have 3 vectors. Okay, and obviously that means dimension is 3, so this one is a basis. Okay, now we're going to discussion of that here. 1 1 1 0. Okay, 1 0 1 1, here 1 0 1 1 and 0 1 1 1. Okay, this one be a basis for M2 cross 2R. Understood? This one is a basis for M2 cross 2R. Not a problem at all. Okay, now we also, why this one is a basis? This one is a linearly independent set and obviously dimension A, that means contains 4 vectors and dimension equal to 4, so this one is a basis. Okay, again we write in this way: 1 0 0 minus 1, 0 1 0 minus 1. Okay, 0 0 1 minus 1 and 0 0 0 1. Okay, is a basis for r to the power 4, because this one is a linearly independent set and contains 4 vectors, so this one is a basis for r to the power 4. Okay, again we also see that. Okay, for k equal to 0 1 2 dot 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 n. Okay, pkx equal to x to the power k plus 1 dot 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 x to the power n. Then what happened? Then p0x p1x and dot 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 here pnx. Okay, dot 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 be a basis for okay pnf. Understood? Be a basis for pnf. So we also discuss the several examples for a basis. Okay, today also we discuss finite dimensional vector space, and then we related corollary to this basis, and obviously discuss this one are the example of some basis. Now we also discussion of that. That means we draw some Venn diagram of linearly independent set and generating set and basis. Okay, so we draw. Okay, then we draw Venn diagram. Okay, Venn diagram. We draw it in this way. This one. Okay, this one. Then this one. We write it linearly independent sets. Okay, and this one is the generating sets, and here basis. Okay, these two intersection contains this basis. Okay, and obviously generating set, that means contains this linearly independent set. Okay, so generating set, something some then generating set obviously greater than from, that means number of vectors in generating set greater than from basis, and number of linearly independent set is less than equal to from basis. Okay, so we also draw this one, the Venn diagram, that obviously gives this relation for basis. Okay, we also discuss today. Then we also, that means we erase that portion, and obviously then talk about something related to that topic. Okay, which one? That means if one linearly independent set. Okay, then linearly independent set for a vector space V. V must contain contains must contains less than or equal to the number of vectors in a generating set for a vector space. Okay, understood? Obviously less than or equal to, linearly independent set for a vector space V must contain less than or equal to the number of vectors in a generating set for a vector space. Okay, so we also now discussion, and obviously that means linearly independent set. Okay, linearly independent set cardinality less than equal to basis cardinality. Okay, and less than equal to generating set cardinality. Okay, understood? Obviously for finite dimensional set we discuss in this way. So today I'll stop here. If you get this type of video, please subscribe my channel. If you gives like, please click on like options. If you have any questions, comments, suggestions, write it in comment box. So today I'll stop here. Please follow the video and see the video and enjoy the topics and obviously understand properly. So today I stop here. Thank you.